Hello all. We'll be starting off this. So, welcome to Bangalore Theory Seminars. It is my pleasure to introduce Professor Sandeep today. He's a senior professor at School of Technology and Computer Science at TIFR and is currently visiting Google Research Bangalore. He did his BTech in Mechanical Engineering from IIT Delhi, an MS in Statistics, and a PhD in Operation Research from Stanford. He has extensive research and teaching experience, having worked at several prestigious universities, including Columbia, Stanford, IISc, and IIT Delhi. He has also worked in industry where he headed the quantitative activity of Bank of America's Indian operation and was member of the Bank of America's Executive Quantitative Council. He is a recipient of IBM Faculty Partnership Award and has co-authored papers that have won the Best Paper Awards in many conferences. His research interests lie in applied probability, mathematical finance, Monte Carlo methods, and game theoretic analysis of views. Without any further delay,
Thank you. Thank you. So as always, happy to be in IISc and in CSA. So, okay, so without further ado, so the way, I was giving this talk at the Google Research Week, and then Rahul was there, and he said, why don't I give the same talk here? And I think what worked was I made at least the initial part of it as more like a tutorial. So I've kept it fairly at that level, and I think that's probably always a good idea. Hopefully that will turn out to be true here as well. So I will keep it more at that level to begin with, just to give you a big picture flavor of things. And then we'll discuss some ideas that we worked on, and these are the co-authors, partner with Shubhada Agarwal, Walter Poolen, Kartikeyan Shanmugam, and Arun Chugala. So most of this, some of this research I'll talk about in the next hour, not in the first hour. First hour is more in the tutorial kind of mode, and then if you survive that, then you can kind of see some of the other parts. Please feel free to reject at any time, hoping for that. I'm assuming most of you are kind of familiar with multi-arm bandits. Is that fair to assume, or? Yes. Okay, because I'm still going to keep it simple. But so this is, so multi-arm bandits for sequential learning. The name goes back, I guess, Lion Robbins in 1952, and it was sampling from distributions, and sampling from distribution is called sampling from arms. It has this, you've probably heard this before, it has this kind of casino flavor and motivation to it. For me, I used to think of, this was the imagery I had of multi-arm bandits. So this is a bandit, this is my, I guess, ex-student at TIFR, Sarat, who's an artist who made this for me. And this is a bandit and who has all the things that I consider important. There's a pen here, I guess now it should be an iPad pen, coffee, my phone, and then I had in the back a heavy tail. So we'll see why that fits in, because we'll be talking about multi-arm bandits with heavy tails. And then, of course, lower bounds. So lower bounds are crucial to all of this. All right, so this is what you have to keep in mind. So this is the talk, basically. You're given a few coins that you can sample from, right? They have some probability of heads. Every time you see a head, you get a reward of 1 rupee. Every time you see a tails, you get a reward of 0. You just don't know these head probabilities. You have these 3 coins, let's say. You just don't know these head probabilities. And you want to sample them in such a way so as to minimize your long-term stochastic reward. So how do I sample so that I figure out very quickly which coin has the largest heads probability so I maximize the long-term reward that I get? There I have to explore. So if I don't have 3, but I have, say, 3,000 arms, 3,000 coins, 3,000 probability distributions, then I have to explore as well. I mean, I have to make sure that I don't miss out on something that's important. So explore as well as exploit. We'll talk about this. And then the other problem to keep in mind is to find the best arm quickly and rapidly. So this is now the objective has changed. It's not that I keep on sampling or flipping these coins and I want to maximize my expected reward over long-term horizon. It's more that I'll keep on sampling with the view to very quickly saying, this is the best arm, announcing that. And I've been given some probability of error, say 1%. That's been given to me already. So I will tell you this is the best arm and I'm at least 99% sure. That's the pure exploration problem. So we'll talk about this as well. In this, we have what's called guided top 2 algorithm. So I'll put this in the context and describe the algorithm. This will be in the next lecture. So we'll restrict to simple problems, but and in a way it's nice because it allows you to go deeper in more general conditions. So we'll ask ourselves, okay, under what conditions on the probability distributions can we solve this simple problem? And why those conditions are necessary. So all those issues we can delve into. Okay, so simple yet elegant setting to illustrate the underlying trade-offs and the elegant conceptual ideas. And some of these are really nice ideas, you'll see. And then large number of practical applications, especially in online settings, fit these framework with some adjustments. So it gives you a feel for more general problems that people are solving, including reinforcement learning, non-coefficient processes. And then thousands of practically relevant extensions are based upon these ideas. Creating that point. So just a quick example, this comes from clinical trials. It's important because that's how this problem kind of was first studied by Thompson in 1933 in the medical clinical trial setting. You have a number of different possible drugs. You want to figure the best one as soon as possible because there's real cost to giving suboptimal drugs to patients. Right, so you can imagine the COVID setting a number of drugs you want to find the best one. This is more common, placing advertisements on Google search. So there are a number of advertisements that they can show to a query. They want to show the one which has the highest click rate. So you have to learn the click rate fairly quickly. Or click rate adjusted for the reward you get after you show the advertisement. Construction amongst many options. So the variety of ways you can construct a web. Which one is most attractive? Gets more your eyeballs for a longer time. Recommendation system, so movies to recommend, there are 10 different genres of movies, which one is favored by a particular user. Facebook posts to show. So all that's wrong with the democracy right now and recommendation systems can in some way be attributed to these algorithms. We kind of reinforce and, in some sense, yeah, that's a very interesting problem that there's no real incentive for the industry to change and there's no real guidelines as to how to change. So if somebody wants to think about that, that's also a very important area. Newspaper articles to make your attention, price to offer for additional good, so on and so forth. So let's come back to this problem. So we're given k unknown probability distributions that can be sampled from. Our aim is to maximize expected reward in t coin flips, in t pulls of arms, or equivalently minimize the expected regret, okay, in n steps. So the equivalence is straightforward, I'll come to it. And in particular, what's the best explore and exploit trade-off? We'll see that as we go along. Any questions so far? Okay, so let's go further. So k arms with unknown distributions, mu1 through mu k, and mu I denotes the mean of arm I. To begin with, I'll just assume that the support of distribution is between 0 and 1. And there's one arm without, and the first arm has the largest mean amongst all these arms. Expected regret is every time I pull arm A, an expectation I suffer a regret because I should have pulled arm 1. Arm 1 is the best one. I don't know it, but that's what I want to pull. So I incur a regret which is m of mu1 minus m of mu A. Right? That's every time I pull a suboptimal arm. Okay, so at round T, arm A of T is chosen and reward x A of T NAT. This just means it's a sample from distribution of arm A of T. And this is just the number of samples that generated so far from this distribution by time t. So this is observed where NAT denotes the number of samples of arm A generated by time t. I want to maximize the expected reward, right? Till time big T, I've seen these samples. This is the expectation. I want to maximize this. But now you know that I can write my expected regret. Remember, regret is every time I pull a suboptimal arm, I incur a regret, which is the difference between the best arm expectation, and that arm's expectation. So it's going to be t times n mu1 minus what I actually get, which is this quantity right here. So maximizing expected reward is same as minimizing expected regret. And this I can re-express as, because every time I pull a suboptimal arm, I incur this regret. So it's this time, expected number of times I pull suboptimal arms. So this equation I just want you to keep with you that, if maximizing expected reward is same as minimizing expected regret. And that's basically the mean difference between the best arm and arm A into expected number of times I pull arm A. So when I say minimize expected regret, I'm trying to minimize expected number of pulls from suboptimal arms. That's the name of the game. Minimize number of times you pull the suboptimal arm.
Weighted by these differences.
Weighted by these differences, yeah. And this is going to be our friend to begin with. Hovding's inequality. Everybody here is familiar with Hovding's? I've given this to talk to audiences where nobody's familiar with Hovding's. Very nice, everybody here is. Okay, so suppose each xi is between A and B, ID with zero mean, then the average, which is supposed to converge to zero, takes this large deviation. This deviation is beyond the center limit theorem scaling of 1 by root n. This large deviation probability can be upper bounded by exponentially decaying term given as follows. We don't need to know the exact form, just that it's a tiny probability. That's all we really need to keep in mind. Okay, first let me just, for completeness sake, let me just talk about the full information case. I mean, right now I'm just telling you about the bandit setting where you pull a probability distribution and you see its samples. You don't get to see what happens with the other arms because you didn't pull them. But now imagine living in a world of, say, portfolio optimization. You're given this 5 different portfolios. You invest in one portfolio, you see what reward you get. But you also get to see rewards you would have gotten from other portfolios that you did not invest in. So that's a full information setting. All rewards will be disclosed at each step. Best strategy at each step, it's given here now. But can you see that the best thing to do, more or less, is to pull the arm with the largest sample mean in this setting? You just follow the leader. Whichever seems to be doing well, you just bet on that arm the next time. And why is that the case? So if the rewards from arm A are XAI, I could want to, then probability of regret at safety. So what's the chance that you pull a suboptimal arm? That's only going to happen if your X bar 1P, the sample average of the first arm, is dominated by sample average of some other arm. So you should have pulled the first arm, but you didn't do it. Right? So your expected regret can be bounded from above. Because I just take a union bound here and I'll express that as the upper bounded by a sum. So delta Q into this probability and so on and so forth, and delta K into this probability. And the point of this is, in the full information setting, all these probabilities are exponentially decaying in T. So this term is an order 1 term. It's a small regret in this setting. Yeah?
In a sense, this problem setting is the pure exploitation. Because exploration is not.
That's right, yeah. There's no need for exploration.
For information, you can actually do even work against stronger odds, like even in like the experts problem.
Sure. Right.
You don't really need to assume stochasticity.
Yeah, that's right. That's more in the adversarial setting. Then you kind of do some kind of multiplicative based strategy.
Yeah.
But this is, I just kind of kept it very simple by keeping it stochastic.
Multiplicative weights might form somewhat suboptimal. This
would be the best. But then with some probability, you're unnecessarily pulling a bad arm.
Yeah.
Yeah.
Pedantic, how do you establish that this is the best? I mean, I'm sure
it may not be, so I actually have not thought about this. It may not be the best, but it won't be very far from it. In many settings, sample average captures the sufficient information that's there. So it's hard to see something else that would work. So maybe there's a nuance that I'm not doing. But this you can see X bar 1T, let's say X bar 80, so X bar 1T is, it doesn't go halfway. And this guy, so this guy comes down more than halfway, or this guy goes up more than halfway. Because if they don't even meet halfway, then there's no confusion. Things go wrong and these things, and both of these we know from Hovding are decaying exponentially. So we get order 1 here. Right, so this was a simple case. This was just to kind of get things started. Let's talk about, now let's come back to stochastic regret minimization problems. Now we just see the output from the arm that we pull. And let's do some simple strategies. So suppose each arm is given, so I'm confusing between small n and big T, but this is the total number of trials. So suppose I'm giving each arm equal number of samples. Right? Then it's clear that most of the time I'm pulling the wrong arm. Right? So n by k times I'm incurring this regret for each A. So my regret is linear in n. Right? So obviously a bad strategy. BD strategy, now let's do follow the leader in this setting. Could I show you that next slide? What do you think will happen if you do follow the leader in this setting? What could go wrong?
Your samples might be off.
Yeah. Can you make it more concrete?
So you might commit to a wrong answer at the very beginning and then
Stick to it. Think of it as kind of Bernoulli trials. One arm has probability 0.9 of heads, 0.1 of tails. Other arm has 0.6 of heads, 0.4 of tails. The first arm has bad luck. First outcome is 0. Second arm has good luck. First outcome is 1. 0.6 times 0.1. So with 6% probability. Now you'll never pull the first arm. But it's 0. The other arm will always be more than that. So you can't just do follow the leader. You need to do something more clever. That's the point here. Regret is, then you can do a slightly more sophisticated analysis. But the point is, there's a constant times n regret. So again, you have linear regret in this case. So the question is, can we get rid of this linear regret in this setting? So is sublinear regret possible? So let me just motivate this to a very simple setting. Explore, then commit. And now let me assume that mu1 might, so let me assume there are two arms only. K arms, except that we have K here. Actually, this K should be 2 here. And mu1 and mu2, mu1 minus mu2 is known to me. So what I'll do is I'll sample each arm a well-chosen m times. Suppose you're, well, you can't become a president of BCCI, you're not well connected politically. But suppose you're kind of a selector of a cricket team. You'll observe some people for some fixed number of matches, right? And then you'll decide what your team is going to be. So you'll explore for some time and then you'll exploit the team. So here you observe these arms for m times, sample them equally m times, right? Then thereafter sample the arm with the best observed sample mean for the remaining. So I'll come back to T now. T minus k m times. The k is okay. Number of arms in this case is 2. So let's come back to two arm settings. So suppose they were Gaussian distributed with mean mu1 and variance 1, mean mu2 and variance 2. Then I will incur this much regret for sure in the first m stages. And with at most this probability, so I have a bound on the probability, with this Gaussian sample I'll make a mistake, right? I'll get the sample average wrong. So with this probability, I'll incur this t minus 2m into, this is the regret I'll incur expected. Yeah.
In the previous example, you mentioned Bernoulli variable. Is there any, but here you said the support was 0, 1 continuous.
That's right,
Is there
yeah.
broadly any difference between 0, 1 versus like 0, 1 continuous? Or they should not?
I mean, some constants will change. So both 0, 1 Gaussian with variance 1 and Bernoulli 0, 1, they're both sub-Gaussian variables. You study this sub-Gaussian setting where you assume that the tails are bounded by this Gaussian decaying term. The constant next to it will change. And that will affect the efficiency somewhat. But yeah, it's just on the constants. Okay, so now I'll optimize on m. And now you can see that optimal m should be log of total number of steps t into mu1 minus mu2 upon 4, this one right here. And if I explore for this much amount, so log of t amount, if I'm going to play t matches in my cricket match, log of t times I'm going to explore, right? And then my regret is going to be again some log t into all these constants here. So the point of this is simply to show that logarithmic regret is possible. What we assumed here was, so to get this m, I need to know mu1 minus mu2, and I need to know t. So I need to know a lot. So then you ask yourself, okay, can I come up with an algorithm where I don't need to know all these things? So I'll go like this for now. I'll show you those algorithms, and then we'll get serious. And then we'll talk about, okay, what's really going on and how we solve this. That time you get Jacob to bedrock.
But that is sort of counterintuitive. The fact that the upper bound is reciprocal with the difference is somewhat. So if U1 and U2 are really close, you would have argue that the regret is actually.
It should be higher, right? Because they are competing close to each other, so you end up sampling the suboptimal arm more.
But as a reward, you are still getting high.
That's right. That's right.
I mean, just to like hyperbolically, both are exactly equal in the regret is zero.
It's like, in the center limit setting, when you want to separate two means, you need 1 upon epsilon square samples. But then the benefit you're getting is of order epsilon.
Yeah.
So that's why it's 1 upon epsilon, the denominator still remains.
Yeah, but I guess like the question was more towards like, I mean, I do see this like these parameters showing up in regret form.
Yeah.
But some like what I'm trying to consolidate, at least in this setting, is that it should be some patchwork I can do to argue that if they're that close, then in fact the regret should be.
Yeah. You're saying that something, a crisp argument which brings out immediately why it shows up in.
Yeah.
Okay, it's 1 upon delta square times delta.
Yes.
And now you want a crisp argument 1 upon delta square. And this CLT motivation is not enough for you. It's not getting enough for you.
Yeah.
Yeah. I think presumably with Houghton's one can probably kind of also tolerate a little bit of extra work would be needed.
Sir, I think like if you just put max of this comma t times mu1 minus mu2, it's either this or that.
I guess so. Yeah. Okay. Yeah. I see.
Okay.
I guess the point was that this is an upper bound.
Yeah.
But an alternate upper bound could be just t times mu1 minus mu2. I mean, irrespective of what you do, the regret can't be more than mu1 minus. So fine, like it's the max of this quantity and that, and if that quantity is better, great.
Let's go to when we do lower bound on this problem.
Sure.
So then you'll see that in the denominator you get the Kullback-Lager distance between the two. And that from Pinsker's can be bounded from delta square. That kind of brings out much more nice.
The log here is courtesy normal distribution.
No. So we'll see this more carefully when we go. Log A is more kind of large deviations theory. Okay, so we'll come to these problems at the right time. Okay, so successive elimination algorithm, isolating the high probability tubes that contain sample averages. So this is very nice. So let me just show you what you have in this picture. So there are two arms. One has mean of mu1 and the other one has mean of mu2. I'm plotting the samples here. When 5 samples are given, 10 samples are given, 15 samples are given. And this is, with high probability the sample average will lie in this tube here. And for each time period. So the point is I can use Hovding's inequality and construct these tubes. So my sample average will lie in this tube throughout. Right? You give me certain probability. With those certain probability, I'll have all the row paths where the sample average does not lie in these tubes. And with the remaining probability, it will lie in this tube here. Is this clear? So that's going to be the flavor of the exam of this analysis. You will give me some probability which is of order 1 upon t. So that if I go wrong with that probability, my regret is of order 1, t times 1 upon t. So I don't worry about what happens on those low paths. And now on these good paths, it's very easy to see what needs to be done. Picture is much more clear. So let's play with that. So the algorithm is successive elimination algorithm. It works as follows. What we'll do is for each arm, we'll compute this upper confidence bound index, so which is x bar at plus alpha t. That's the height on that tube which I showed you at time t. It's square root of 2 log t upon 2 log big T upon t here. So I get this upper confidence bound and I get this lower confidence bound. And now the algorithm is straightforward. Eliminate arms for which, so what I'll do is I'll generate equal number of samples for all the arms. And whenever I've lost hope in an arm, you see the AT is less than max A LCB AT. So upper bound for some arm is less than lower bound for some other arm. I throw that arm away. Right? That's the algorithm. And then if a single arm remains, then assign remaining samples to this arm. So that's the successive elimination algorithm. So what's a regretter? Well, first let's just see why it's a good thing. Best arm 1 will never be rejected on the good set. So I've given you a good set now. And the claim is that at least on the good set, best arm will never be rejected. That will happen only on rogue paths, which don't really matter so much. And then all the other arms will be rejected on this good set. That's the spirit of things. So on the best set, on the good set, arm 1 will lose if x bar 1t was less than x bar at minus 2 alpha t for some t. And only then will it lose. And we know that x bar 1t is greater than or equal to mu1 minus alpha t, which is greater than or equal to mu a minus alpha t, which is greater than or equal to x bar at minus 2 alpha t. Right? So at least this arm is not going to get rejected, just by the design. So any question on this? Okay. And then
This setup, we are still sampling all active arms. Right?
That's
Each
right.
time instance.
That's right. There's equal number of active arms until some gets rejected, carry on like this. One arm remains, then all the samples they are from that. Suppose arm A is rejected, so to get an idea of what the regret looks like, how many times did we sample a suboptimal arm? Suppose arm A was rejected after sample t plus 1 times. That means the time t was not rejected. That means mu A plus 2 alpha t, which is on a good set greater than or equal to x bar at plus alpha t. And since this arm was not rejected at time t, this was greater than or equal to x bar 1t minus alpha t. Otherwise, it would have been rejected. Right? And this is again greater than or equal to mu1 minus 2 alpha t. Right? So this, mu1 minus mua, I'm calling it a delta A. So delta A is less than 4 alpha t. So now I'm calling it big T, I'm calling small n now. This n is the time at which, I guess, t is what I'm calling n. But in any case, the number of samples that I've given to this suboptimal arm is less than or equal to 32 into delta A inverse square into log of.
Is n the number of, is n t or n is like the number of samples until time?
N is number of samples that have been given to, it's to the suboptimal arm.
Like in the previous setup where you sampled all arms, it will be like t times number of
T
arms.
times.
Here it is less than that, right?
So, so I'm kind of being a little precise, but all I'm saying is that the suboptimal arm, suppose it was rejected after t plus 1 samples were given to it. So then what happened at the tth, when the tth sample was given, this relationship was true. And that tells me, okay, that the t must be less than this quantity here for each suboptimal arm. And now when I sum it over all the arms, then I get a problem with the regression. But the point is, now I got log of t here without knowing the mu1 minus mu2, all those things. So I can get this to work. And the question then is, okay, we were sampling all these arms equally. Could we have done something more clever? Right? So that's also straightforward here. And that's your UCB algorithm, upper confidence bound. What it says is, at each step t plus 1, select an arm with the largest value of the index. So for each arm, at every time t, I'll have some index. And I'll sample the arm with the largest value of the index. That's what I'll keep doing. That's my algorithm. Yeah. Regret, right? Total expected regret. So I'm going to multiply this by delta A and then do the summation. Okay. So this is my index now. So x bar at sample average that I've seen, and alpha of NAT, number of samples I've seen of arm T, and that's given by the alpha T is given by the following parts here. At least, okay, so this should be NAT here, T here, and NAT in the denominator. So T here and NAT in the denominator, that's what comes in this index here. And the point of that is, if NAT is fixed, if I'm not sampling this arm, then this log of t keeps on increasing, so this index keeps on increasing. So if I don't pull the arm for a long time, the index value increases. If I pull the arm many times, so I have NAT here, if I pull it many times, then this index looks a lot like the sample average expiry. But let's just see the whole picture from this good set viewpoint. And the point is this. My index for every arm on the good set, this index is going to be greater than the mean of the arm. So no matter how many times I've sampled it, the index will be greater or equal to mean on the good set. So first arm's index is going to be more than mu1, right? So now the second arm's sample average is here. If I add alpha t to it, it's here. So after this point on the good set, the second arm is never going to win. Right? So it's as simple as that. So basically, earlier it would have been, okay, when these two arms were well separated, then I would have thrown away this second arm. Here, I basically stopped sampling the second arm after this point. So much earlier, so much lesser regret. So that's the intuitive feel for it at least. Okay, this is the real picture with the actual data. This is the mean is 2.5. This is this is I guess that plus minus alpha t confidence interval, and this is plus minus 2 alpha t confidence interval there. And the point is this. Let me see what point I'm trying to make here. The point is this: my x bar t for second arm is here. So x bar t plus alpha t. No, my x bar t is here, and x bar t plus alpha t is here. So this is where I would have pretty much stopped sampling the best arm. But if I had carried on my previous algorithm, then I think around this point, x bar t plus alpha t and then x bar t minus alpha t. After this point, I'm sure that I will not be sampling this arm in the earliest accelerated reaction. So basically, between this and this, intuitively, that's a flavor of the benefit that I got. Okay, so just some more things about upper confidence bound algorithm. So for an optimistic upper confidence bound on each arm, this UCB is greater than the sample average, but converges to it as the number of samples increase. So it also gets closer to a true mean because the sample average gets closer to a true mean as the number of samples increases. It increases if arm is not sampled for a long time, so this encourages exploration. And the algorithm simply involves sampling the arm with the largest UCB index. Right? Now you can show with the simple analysis that expected number of suboptimal arms is going to be 8 times log of t by delta a square. Then some constants. So from 32 you go down to 8 in the upper bound. Yeah.
So the alpha that you computed involves knowing capital P.
Yeah.
But if you do not know it,
no, in this case for UCB I kept it as small p. So it does not matter. You can some constants will have to be adjusted, but you can still construct that tube using Hopkins, even by having small p. Right in the Hopkins, you get 1 upon small t square. You sum that up, you'll get okay. It'll be suppose it was 1 upon small t. You sum it up till time big T. It is still bounded by big T. Okay. Right. So now we get a little bit more serious as to what's really going on.
So, the confidence bound here is again inspired by inspired by Hopkins.
By sorry?
Hopkins and equal. Hopkins.
Hopkins, yeah, that's absolutely. Right. So we'll come to this, KLUCB now. We'll talk about that a little bit more. It's basically these are the things which are giving us the right concentration inequalities.
One question.
Yeah.
So in this Hopkins inequality, you assume that the random variables are bounded between these A's and B's.
That's right. Yeah.
But if we had some unbounded case with similar results,
if you had that heavy tail, you think?
I don't know. That in general.
So the whole talk is about the heavy tail. Yeah. So the tail is not bounded; it's heavy. But yeah, exactly. Those are issues I'm going to talk about. So we'll now get serious and look at things in a little more serious. So algorithm was good as the guarantee. So we'll first define good algorithms. So what are good algorithms? Which have a regret of small o t raised to power alpha for all alpha greater than 0. We're just saying these are algorithms you're going to call as good. Now this is for any alpha greater than 0. So regret of log square t, log to the power kt would fit into this setting. But this is fine because we already have algorithms which are good. We've seen some of those algorithms. It's not a big restriction. So we'll restrict ourselves to these good algorithms for any mu is a vector of means or vector of probability distributions lying in this universe of probability distributions L. In this case, the universe is all the distributions suppose 0 to 1. So for these kinds of algorithms with these guarantees, Lai and Robbins in 1988 came up with a lower bound, and Vanetta Katehakis in 1996 generalized it. Basically, the suboptimal arms, number of times you pull each suboptimal arm A in total trial T, must be at least log of T divided by Kullback-Leibler between mu A and some other distribution, and the way to find that constant here is it's going to be KL infimum. So we'll look at KL between mu A and distribution mu, where mean of distribution mu is bigger than X in this case. So in this case, I'm going to look at all the distributions whose mean is more than mu1. I'll look at their KL distance, and I'll take infimum of that. That's what gives me a lower bound. Okay, so now let's understand this lower bound a little bit better, more intuitively.
Sorry, what is the distribution associated with mu A?
With mu A, so mu A here is a probability distribution. So you specify upfront what your family is. So in this case, for example, so I'll talk a lot about different families and what we say there. But for now, you can think of it as any distribution which has a support between 0 and 1. So mu A is any arbitrary distribution with support between 0 and 1, and that's true for all the arms. So now I'm going to look at all the distributions whose mean is more than mean of the best arm. Right?
I'm a bit confusing. KL divergence is two distributions. So I understand mu.
Yeah.
Right. Now, what is mu? Like the first distribution in this function here?
Yeah. No, so thanks. So I'm being unnecessarily fast here. Let's understand this quantity KL infimum. So what this means is let's look at KL between two distributions, mu A and mu. Okay. And I'm defining this for the second argument, which is a real number X. This is not a distribution. So I'm going to look at all the distributions mu whose mean is bigger than X. And I find this Kullback-Leibler between these two distributions. And I'll take an infimum over all these distributions. And that's my KL int mu AX. And that will become, here X is M of mu1. So all the distributions whose mean is more than the mean of the best arm, I'll take the infimum over those guys. Is this clear? Yeah. That's my lower bound now.
I mean, intuitively, it's saying the closest distribution is the mean more than the closest to the arm distribution. Because in some sense, the most effort you'll have to exert to distinguish between these.
Hardest one to separate.
Hardest one to separate.
Exactly. That's precisely the idea. And that's the game. You're trying to separate. This is like testing a hypothesis. Like you want enough samples, enough evidence to separate, and then you can rest. Okay, so let's use Sarnoff's theorem. So does everybody know what Sarnoff's theorem is here? Okay, finally something here. Everybody's like pulling the head out of us. Okay, so this is from large deviation theory. So suppose that true distribution is this green distribution mu. So there are 4 support points, x1, x2, x3, x4. And this is the true probabilities of your underlying distribution. Okay. And now you generate lots of data, n sample points, and you see a sample empirical distribution. And you say, empirical distribution should look like this green distribution, right? This kind of a law of large numbers, this tells you that. But what's the probability that looks like this red distribution? Okay. So that's the question we're asking. Underlying distribution is mu. What's the probability it looks like mu? That's what Sarnoff's theorem answers for you. It tells you roughly that this is going to look like e to the power minus n, and Kullback-Leibler distance between mu and mu. Mu comes in the second argument. That's also very important. So mu is a true distribution, and it looks like mu. So that's given by KL mu. It's a good way to absorb the notion of Kullback-Leibler distance. What exactly are we measuring? So this derivant theory, large deviation theory, gives a very good idea of this. In this case, as you know from the definition, this is what KL mu means. Mu I log mu I by mu I. Right? So you're with me on this? So we'll use the Sanoff theorem basically. So what's going on? So heuristic argument for the lower bound. So I'll give you a heuristic argument. It's actually very easy to make it precise and rigorous using data processing inequality. I won't talk about data processing inequality right now. We can kind of maybe offline take it up. Yeah?
In the previous, sorry, if the infimum is over all the x which have mean over the minimum, what is mu A?
Mu A is the distribution A. This is for arm A. Right? What's going to happen is the data is coming from distribution A. Right? And you want to rule out the fact that it's probably coming from some other distribution which has mean m of mu1. Like only then will this be suboptimal, right? So that's what you want to rule out. So you need these many samples at least to rule this out. And this is an asymptotic result as t goes to infinity.
So you want to do this for all arms?
You want to do this for all arms. So that's why, I didn't make a big deal about regret being weighted sum. It really just boils down to understanding how many suboptimal arms you put. Okay, right. Is that okay? But this will kind of concretize what I'm trying to say. So algorithm is concerned that data are coming. So for arm A and 1, generated samples with high probability are close to the true distributions. By law of large numbers, I've generated samples from arm 1, I've generated samples from arm A. They're very close to the true distribution with high probability. But algorithm is concerned that the data from distribution nu with m nu greater than m mu1, algorithm is worried that although it looks like arm 1 is the best one because it's close to network, but it might actually be coming from some other distribution which has a larger mean, and what I'm seeing is a large deviation that is happening. Right? So if indeed what I've seen is a large deviation, I want to control the regret I'll get from it. So evidence needed, so regret from potential error is small. So if ft is the number of samples I give to arm A, chance that arm A is from distribution mu, but the empirical distribution looks like mu A, I can approximate it through Sanoff's theorem, e to the power minus ft, Kullback-Leibler, mu A and mu. So I'm worried that the true distribution is mu, but it just looks like mu A. I'm seeing that the data looks like it's coming from mu A, but maybe that's just a hallucination in the current world's language. It's actually coming from mu, right? So this is the probability here.
Very quantified.
Yeah. I like, yeah, that's right. Yeah, it's very sweet, this way of looking at things. This probability I want to keep at the level of 1 by t. Because if it's at the level of 1 by t, then the regret is going to be of order 1. You can see here, I want ft, so error probabilities of order 1 by t. If probabilities of order 1 by t to the power alpha for alpha less than 1, if it's 1 by square root t, then my regret would be of order square root of t. But I have a good algorithm. Good algorithm is not permitted to have this regret. So I look at regret of the order 1 by t, and that tells me that my f of t should be greater than equal to log t upon Kullback-Leibler of mu A and mu. It's a very heuristic argument. You can derive these things very precisely, asymptotic as t goes to infinity. And the tool is data processing inequality. You can discuss that later. So is this clear that, I want to rule out every such distribution when I look at the data. Every such distribution would mean it at least m mu1. That's how I get this one. So that's one part of the story. What's the lower bound? How many samples I need from each arm to be convinced that they're not coming from the, that they could not have been the best arm. Now the question would be, now that I know this, how do I devise an algorithm which actually matches the lower bound precisely? Not precisely as t goes to infinity. Not getting it constant. So we'll do this. So we'll look at KLUCB algorithm. So this was first time it came up in 2013. As is everything in this world, 3 or 4 people came up with a good idea at the same time, then they had to combine together and write this paper. This is a difficult community to be in. Every 2 weeks you get school. In any case, so KLUCB, but they came up with this algorithm for Bernoulli family, basically, Bernoulli distribution. A slightly more general version of it, single parameter exponential family. So where you just need a single parameter to describe a probability distribution. Like a Gaussian distribution is variance 1 and mean mu1. The advantage then is I can replace the distribution by its mean. So it becomes a nice single parameter problem. The analysis is much simpler. So this is what these guys had done in 2013 just for Bernoulli distribution. But Guhan here wants to do this for much more general distributions. So that's what we did. And what we do this is for all distributions whose 1 plus epsilon moment is bounded by some fixed constant b. And we'll argue that you need this assumption. You can't, we need to know something like this b. Otherwise, you're going to be in trouble. Yeah.
Sorry, I missed that part. What are the conditions under which you can replace the distribution with the parameter?
Single parameter exponential family. So the family is described by a single parameter. So Bernoulli, I can just replace the Bernoulli distribution by its parameter, probability with which it takes value heads. Gaussian with mean mu and variance 1, I just need to tell you mu and then you know the distribution. So if I restrict myself to just this family of distribution, all my arms are from this family of distributions, then in that set they describe the KLUCG algorithm. But we'll expand that universe to allow for all distributions which have this kind of a bound on them.
This assumption almost looks like very similar, not similar, but almost some sort of vague memories of CLT sort of assumptions and.
This epsilon can be 0.1 also. Huh?
Yeah. So those either those networks say CLT.
No, so there, for example, you just need to know these things to be finite.
Yeah.
We are asking that we have a known bound on them. So we are asking more than what they do. Just being finite is not enough. We need to know this B.
Other than the UCB, the classic UCB you mentioned, because you are not assuming that the random variables have a bounded support, like the small b.
So it's weaker, right? There they assume the random variables are lying between a known bound A and B. Yeah.
So this is a better result.
Much better. Yeah, it's much stronger strengthening of those results. And you need a lot of new ideas, and that's this talk is about those ideas.
But it's not even a second movement, it's just
just 1 plus epsilon moment. And actually one can generalize it. I just need any kind of sublinear, superlinear convex function, non-negative convex function, everything will go through. Something to control the data.
Okay, but isn't it like even for the home teams you get like similar kind of results for if you just are able to bound like I think the NGFs, like you don't need bounded random variables to apply home teams.
So do you think a random variable which has this bound has a finite NGF?
Yeah.
Think of Pareto distribution. PDF is 1 upon x squared, constant upon x squared. NGF will not exist. So your point is valid that Howdings generalizes to say sub-Gaussian distributions. And that's the typical generalization that they do. But we are talking about something far more general than that.
These things can have substantial tails, whereas like putting is for sub-Gaussian.
That's right. So the tails are much bigger. Interestingly, in this, so what I'm solving is, right now I'm still in the regret setting. But interestingly, tails don't play as big a role as you'd imagine. Because we are able to resolve these things. But I don't have a punchline right now to explain to you why. Let's just carry on. There is, I used to have it. I don't have it.
I mean, it is somewhat surprising, right? Like the current understanding, like so far what you have talked before the KL and the large deviation. It is somehow as if proofing is guiding the entire. The confidence bound, like every picture, like the analysis, the intuition, everything. So it's kind of, and it's known that it would not generalize beyond sub-Gaussian.
So we will generalize it.
No, yeah. So that's sort of a
true.
That's a surprise element.
It is a surprise element. We've written many papers which are wrong. And in 2011-12, we wrote that this best term this was not the regret minimum, it was best term setting. Why it becomes enormously difficult because the tails are heavy tailed, and if you see heavy tail, everything breaks down. But the truth is, we were able to actually solve the heavy tail problem later in 2016 or so. So I can show you the mathematics of it. I don't right now have a crisp explanation. I mean, it's clear that heavy tails don't play a role as the way you think they would. But beyond that, I don't have a crisp explanation to kind of nail that point.
Those are the best results, right? The ones that you think are wrong.
Yeah, yeah, no, absolutely. The only thing was, yeah, so this was, in the regret setting, heavy tail stuff was already done by some other people. But they had a different kind of algorithm. Our algorithm is better in a very specific sense. In the sense, our algorithm is optimal, theirs is not. But it was already done. So, in the regret setting, the surprise element was already taken care of. But in the best term setting, yeah, this was kind of something that was very good. Okay, so this is interesting that why do we need some condition like this existence of moment bound B? Because, if my true distribution is this green distribution here, I can take some mass from it early on and at a well-chosen point throw it in the tails. And if I do this carefully, I can have two distributions which are arbitrarily close in the Kullback-Leibler sense and arbitrarily far in the mean sense. So these are kind of inseparable distributions. Okay. So to basically get rid of these inseparable distributions, I need some condition. And this bound B achieves that for me. All right, I should probably end. Maybe can you give me 5 minutes, or some people have to go home. Okay, so I'll finish this part of some of the key ideas which I want to mention to you. I'll bring them together, then we can kind of take question answer, and then we also have a next session. So the algorithm just follows. What I'll do is for any arm A, I'll construct an index like in UCB. So I have this mu hat A, which is the empirical distribution. So I'm looking in the space of empirical distribution. I'm making this Kullback-Leibler ball around it of radius log star T upon NAT. NAT is the number of samples that I've had so far. So I'll collect all the distributions which are this close to mu hat A. Amongst those distributions, I'll find the distribution with the largest mean. And that's my index for arm A. So this was the idea people had used a single parameter exponential family. It generalizes to this setting as well. But yeah, it's probably, once you observe it, it makes a lot of sense. In any case, is this clear? And now the algorithm is pull the arm with the largest index at each step. That's the algorithm. Yeah, it's log T, maybe some extra terms here and there. We don't want to focus on them. So some log T terms. Okay, right.
Right now, this is like it will probably circle back to how you do this computation. Or in particular, how do you compute this?
That's right, yeah. So that continues to be a drawback. So there are enough monotonicities here that you can come up with a polynomial time algorithm. If you want epsilon error in computation, then it will be polynomial in 1 upon epsilon. So those algorithms are there. In that sense, the problem is still doable, but practically it takes a long time. One needs a kind of better set of algorithms. I use some ideas in the directions which would work, but not fully developed so far. Okay, so why heuristic arguments? So all indexes typically dominate their mean. Just by definition, mean is going to be part of this whole ball. Yeah.
So n-K's constant need not be hyperplane.
No, that's it. Yeah.
And just asking, therefore, maybe this was already asked, but identification of this index for MAR.
That's right. It's computationally intensive, but if you want epsilon error, you get it in a polynomial in 1 upon epsilon. I think 1 upon epsilon to the power 4 or something. All these bisection algorithms you can develop. A lot of monotonicity.
Any continuity arguments?
You require continuity arguments too. Yeah, that you get. And this is nice because you need continuity in the space of probability measures. So the Kullback-Leibler as a function of probability measures should be continuous. So you use the Levy metric of probability measures. In that metric, we show this continuity. So it becomes technical.
What's the difference between these two papers? One is 2011, one is 2021.
So this one did it for single parameter exponential family, and this is it for general distribution.
Just to confirm this 1 plus epsilon moment being bounded is sufficient to guarantee this existence of this maximum.
That's right. That's right. So all indexes typically dominate their mean. The mean is inside that ball with very high probability. So at least one index will get P by K number of samples. So then for that index, you're concentrating around the mean. The ball is concentrating because you've got enough samples. No, log t upon t by k. That's a very tiny number. So its index is close to its mean. So if one index is close to its mean, so arm1 must get most of the samples. This must be arm1. It can't be some other arm which is getting, because all the other indexes are bigger than their mean. So it can't be that the smaller mean is concentrated. So it has to be arm1. And then once you've got that, then you look at this. What's really going on is as follows. For all the other arms, you keep on giving them samples until this guy touches the best arm's mean. And then, no, you don't give it samples, and its index increases, the ball increases until it touches the best arm's mean, and then you give it an extra sample there. And then the index comes down, then it rises again until the gain is comparative with the best arm's mean, then it gets a sample, comes down. You can imagine, it's not difficult calculation, that in stable situations, this will become an equality here. So NAT will look like log t upon Kullback lambda mu hat, and this kappa will be the distribution corresponding to the mean of best arm. So you'll achieve the lower bound. You can actually see these things here. Yes, NAT will look like log t upon here. This can be computized.
It's the this would require data to PPI.
This argument, I mean, the intuitive argument does not. The mathematical argument still requires it. That's our tool to answer. But now, all of this, to do the regular analysis, you have to worry about these things. It requires bounding the time suboptimal arms are pulled. So you have to look at this self-normalized sum. So, and you have empirical distribution is converging to the true distribution. So you can imagine that the distance, the scale int from n mu way is going to be 0. And if this was true distribution here, this would be 0. So this is a large deviation that's happening. This is a kind of a tail event that's happening, so it requires a concentration equality. And if everything boils down to getting a concentration equality, and you want these uniform anytime concentration inequality. There exists time t where you see this deviation, you want to bound those probabilities. Because we are dealing with stopping time in this case, right? When I pull this arm, when I pull that arm, these are all random. So it's these uniform bounds which help me kind of do analysis in this work. So then I can deal with these adaptive strategies. So what are the tools and techniques one needs to do these uniform bounds? Let's talk about that now. So let's understand KL as an object. Right? It's just this Kullback ladder between eta and kappa. I'm optimizing over kappa and minimizing it. I want under kappa distribution this moment constraint to be satisfied, and I want the mean to be greater than equal to x. And kappa is the distribution. Right? So it's a nice convex programming problem. I can look at its Lagrange dual. Right? Let me show you the form of that. It's very interesting. So under eta, it's an expected value of log of 1 minus x minus small x lambda 1. This quantity lambda 2. Lambda 1 and lambda 2 are such that this quantity here is always strictly positive. I mean, this requires analysis to show, but this is what it comes out to be. For empirical distribution, if eta is an empirical distribution, because that's not going to have the algorithm, this quantity looks as follows. So it's sum of log of these terms here. So this log is coming up here. So this kind of takes away the tail effect. These xi's are fat tailed, but log makes their tail lighter. Now, so what's the crisp answer? I'm optimizing the first argument, I guess the second argument here. If I was optimizing the first argument, if you've seen Gibbs measure and all that, then the optimal solution will be an exponential twist, which will not exist for fat tail distribution. But now it's a different kind of twist. I don't have a name for it. Basically, the original distribution divided by this quantity here, normalized it's a new distribution. So it's a different kind of twist. But this twist exists even for these fat tail distributions.
Does it will have any interpretation to it?
It's very useful to us. I don't have an interpretation for it. I'll tell you how it's useful in a moment. But the argument that I was looking for, and I think I had it long time ago, it's with this Sarnoff from the way we are implementing it right now, it doesn't cause the kind of damage that it would have. Because we are optimizing on the different argument. But let's leave that aside. I won't be able to say any more. But this quantity, I just want to show this to you here, because I have, if it was just this quantity here, then it's average of IID sums. And even if NAN is a random quantity, it's still a martingale. I can do all that analysis. So I have all those tools available to do it. But I have this maximum sitting outside. Lambda 1, lambda 2 lying in some compact set. This set, where this is non-negative, it's a compact set. So this is the object that I have to play with. I have to find a deviation inequality for this object. I have to show that this can't take large values. So that's a challenge at hand. Now, naively, what you do is you build an epsilon net on this compact set. And then you have lots of these IID variables, and you kind of then handle each one of them. This is what we did first. This is in our earlier paper, 2019 or something, for the best arm setting. For the regret setting, we came across, basically through our co-author, some new set of tools which are very elegant. So let me explain them to you. So what you need is this, suppose I had this sum of exponential concave functions. So this function, if I exponentiate it, I get this linear function in lambda 1 and lambda 2. So that's concave. So this is an example of sum of concave functions. So let lambda be a compact and convex subset. Let Q be a uniform distribution on lambda. And GT is some concave function. All I'm saying is that if I've given you this sum of x concave functions, then looking at the max, I can upper bound it by doing this some clever analysis by log of expected value of this term. So where lambda is now distributed, it has some probability distribution, uniform along this compact set, and then you incur some cost here. So let's understand this. See, this max cannot be dominated by this expectation. Right? If you remember Laplace's principle, you have this integral and you express it, most of the mass is coming at the maximum point. But clearly the maximum point is going to dominate the integral. But the point is because of this concave structure, they're not too far apart. So this is the pocket change that we get to use, and this goes back to some kind of results that you see in Cover's time for universal portfolios, but Santosh Venpala and others had done this in early 2000s. That's where we kind of see this inequality. So why do we want an expectation here? It's very interesting. Because when I exponentiate this quantity here is actually a super martingale. It's first of all, it's non-negative. This I'm looking at those values, lambda 1, lambda 2. Xi has mean mu1, so mean 0. This guy has a higher mean than this guy. So it's going to be a super martingale, non-negative super martingale. And I'll have product of non-negative super martingales. So if I take expectation of super martingales, that's still a super martingale. And with super martingales, I can do concentration inequalities. I have tools and techniques for me, and I'll show you Wheel's inequality. This is exactly for getting anytime concentration inequalities for super martingales. So I have those tools. So this is, if I have this expectation, then I'm in good shape. If this max, it is causing troubles. And with this inequality, I can get this expectation. So that's the big idea here. So the latter is a mixture of super martingales and hence the super martingale. And I won't go into too much detail, but let me just tell you this Wheel's inequality here. For a non-negative super martingale Mn, how many of you have heard this, used this inequality or heard of this inequality before? You have. You both have, I see. So it's common in computer science. No, it's fascinating because we study probability theory. I think Chandra would back me up. Dub's martingale theory. It's all about Dub's some martingale theorem, some martingale inequality, martingale stopping time theorem, divergence theorem. Nobody studies these Wheel's inequality for super martingales. And it turns out that Wheel's inequality was there before Dub's time. So he saw this and then kind of realized that martingale is an object to be studied. So this was an inspiration to him that, why focus on martingales? I guess maybe, we go with this. The proof is very simple of this. It's just a couple of lines. So there exists an n, so Mn greater than equal to x is bounded from above by u of n0 upon x. So this is how we get concentration inequalities, which are equivalents of Hövding's in this setting. And then we can do all the analysis here. And not just here, even the next problem that I'll talk in the next session. Let me just make one more point before I end, and it's a beautiful point. So if you see another very nice result is Dawson-Verdhan representation of KL divergence. And how many of you have seen this before? KL between mu and mu is supremum over all measurable functions of expected value of g under mu minus log of expected value of exponential of g under mu. So you look at this quantity, take the supremum, that's another representation for KL mu. You stare at this and you realize that our algorithm, our index is based on plugging in KL in the KL UCB. And that's the supremum of these things. So a thought that immediately comes to you is maybe the other indexes that exist are specific G's that have been used. So with the specific G's, you get larger indexes, and hence they're suboptimal. And this guy is optimal, this guy actually matches the lower bound, they don't match the lower bound. So this becomes your tool for coming up with new indexes. So for UCB, you can actually come up with the right G and recover UCB from here. And I think there was this kind of robust UCB version for heavy tail. With some manipulation, you can recover that also. But this is something very useful to keep in mind. So again, KL comes in here, it has this representation. Index here, so KL is supremum of many things. You take any particular G, you get a bigger confidence interval. Bigger confidence interval means you'll pull the suboptimal arm more times. Optimal arm, in any case, you're sampling a lot. You don't have to worry about its deviation. And so that's the intuitive way of thinking about this. Okay, let me end here. I think after some time we can start the next lecture. Any questions on the net? Anyone? No question. No question. Okay, good.
One is in practice, like if you compare classical UCB and your UCB, and for sub-Gaussian, how does it perform?
Probably ours is very bad.
Bad.
Yeah, ours is horrible. Yeah.
No, not computational point of view, but even the regret bound.
Oh, no. Regret bound ours can be much better. So, for example, robust UCB that was proposed in 2013 by Bubeck and others for heavy tail random variables, we do about 20 times better than them in a simple setting. Simple arbitrary setting. So, regret is much better for us. Now, you can say that in practice, there could be some application where computation is not so important. In medicine, you want to make sure that the regret is minimized. Then these algorithms become more useful.
In function sampling, I don't know, how does it perform in practice in this kind of baby?
Yeah, so that people tell me that they're thinking of a Thompson sampling version in the heavy tail settings. It's not come out so far. So Thompson sampling is all about bounded random variables, etc. Right? You start with beta distribution or sub-version and all that. So there's no version right now for heavy tail variables. But one wouldn't be surprised in a couple of months if you see some paper. And that's Adam Bierman, he said he had something on this.
Any intuition for this real inequality? Like it says something about it.
Yeah, I don't know what. I mean, it's kind of like super martingale, right? Huh?
It's Markov on steroids.
Yeah, it's Markov on steroids, but you know, because it's a super martingale, so EM0 dominates EM1, EM2, EM3. So it's just like some martingale inequality which had EMN here coming up here. You know.
So is it not saying that like post some point of post x mn cannot be greater than some value?
This is equivalent to saying the supremum of Mn is greater than this, right? There exists an N is equivalent to supremum
that's
of
right.
Mn.
That's
I
right.
think the proof may go via some stopping time argument.
It goes to stopping time argument. It's a very simple argument. It's 2-3 lines, and like you see for some martingale inequality. So, yeah. But I mean, the point is exactly it's supremum of Mn, but Mn's themselves on average are decreasing. I can show you the proof slide. Your slides.
Exponential interpretation of looking at like an optimization problem with like a sampling surrogate. So the third wheel in this whole is this volume estimation. Does that perspective, like Vampala's work, for example, like how they built on Cover's idea, or even like this paper by Hazan too.
Yeah, this was the Hazan and Vampala paper. Yeah.
So they also have like a volume estimation perspective. Like the three are like similar problems up to certain factors. Does that help? Like looking at it as some sort of volume estimation, but in this case,
Hard for me to say right now. I mean, yeah, it's probably worth thinking further. Probably not about this one.
yeah, so sometimes you actually want to do volume estimation, then realize you can express it as a, like the other direction is also
I
something.
see. Wow.
You start with computing some expectation and say that you can.
The expectation, the volume, but then you get maximum
Yeah.
optimization problem, you can say a lot about that. Right?
Other direction. Visualize something.
Yeah, no, this was something, the community knew, and Wouter Poolen was in the community, so he could point us to that reference, but this was not something he was actually thinking about. But it's very powerful, yeah.
We got scooped on this exactly. Very different context.
I see, I see. Unfortunately, we didn't get scooped this time. So we'll start in a few minutes again. Yeah. What is next? What is it?
So we have 2 downstairs. We'll meet again at 6.
At what time?
For 35 5.
5:35, I guess.
5:35?
Yeah, we'll meet.
By this watch, actually it's 5:15 right now. So by your watch, 5:30. So am I imposing or?
Can be flexible. I think it's the same crowd.
Okay, whatever you want. Yeah. Yeah, so I should probably close this, right? Anyone bother out of saying that? Anyone ever bother out of saying that?
Yeah, it's a bit of a hazard.
What happens so far?
Not philosophy.
Is it over or no? It will be continued. You can stop recording also.
Get like better boards.